welcome back. It's a new week, and I'm here with a new chapter. And this chapter, we're going to go through reactions of alkenes and alkynes. But before I start, writing actually a bunch of chemical reactions, I want to highlight the most important factors whenever we are dealing with these molecules. How can I predict whether this reaction is going to go almost 100% completion, or like what type of product I'm going to get? How many of them? Which one is the major or which one is minor? Okay, let's go after it. And we're going to start with enthalpy. Enthalpy is the amount of heat that one reaction might get or lose during formation of product. So the gap between reactant and product, we call it the delta H of the reaction. Remember, whenever you are turning a reactant to a product, you're gonna break some bonds, maybe. Okay, and a breaking bond requires energy, so you have to give it energy. And the amount of energy that you spend to break a chemical bond, we call it bond dissociation energy. Okay, bond dissociation energy. And if our reaction is producing heat, then in that case we say it's exothermic. Or if in order to do the reaction we need to apply heat, in that case we say it's going to be endothermic. So exothermic heat is exiting the system. If I'm the system, if I'm the reaction, heat is exiting the system. Endothermic heat is entering the system. Okay, let me go through these two graphs and show you the difference between them. So the first one that we have is methane. We know if we burn methane, we get CO2 and H2. That's a combustion reaction. I want you to highlight position of reactant and product. Reactant is sitting in higher level than the product. So product are sitting lower level of energy. We have delta H versus reaction coordinate. And if I go and measure the gap between reactant and product, I get this. Okay, the gap between reactant and product will be this one. And that's, I'm going to call it Q of the reaction or delta H of the reaction. And delta H of the reaction in this case is going to be negative. What does it mean? It means it's exothermic. So I'm going to say delta H for this reaction, delta H of this reaction is negative. That means this reaction is going to produce heat. So one of your product will be heat. Okay, next, if you go and measure the gap between reactant and the max point, okay, the reactant and max point. So again, let's start from here. So we're going to go after the max point and find distance of it from the reactant, and this is going to be the answer for it. This one we call it activation energy. We show it by EA, so I'm going to call it activation energy. You need to give any chemical reaction this amount, this activation energy, in order to initiate it. Next, what's the max point? The max point, we call it that point, we call it the transition state. Z state. Okay, so the transition state is a technically structure or a coordinate that is this somehow between the reactant and the product. It depends where that transition state is standing. If it's close to the reactant, the geometry mainly will be like reactant, but if it's close to the product, it will be similar to the product. Okay, this reaction, as I said, is exothermic. And next reaction, we have calcium carbonate. We're turning it to calcium oxide plus CO2. And delta H of this reaction, and delta H for this reaction is going to be positive. So I say delta H of the reaction is positive. What does it mean? It means heat is entering the system. So I'm going to write the heat on the left side. We are adding heat to the reaction. Okay. Next, let's find the gap between reactant and product. Okay, and that's going to be the gap between them. And this one will be delta H of the reaction, and delta H of the reaction, it will be bigger than 0. Why? Because the products, this time they are sitting in a higher level than the reactant. And I'm going to add heat to the reactant to make it to the max point, again, which is the transition state. And the gap between reactant and the max point, I'm going to call it activation energy. So this one, it will be the activation energy, and you have to give it this energy. Okay. So again, the difference between exothermic and endothermic is a level of the product. Where the product sitting in exothermic product sitting lower level. That means you are going to generate heat plus the product. Well, when it comes to endothermic, we have to add heat to the system. And as you see, I added heat to the left side, not to the right side this time. Okay. And this is the main difference between exothermic and endothermic reactions. Okay. Next, let's talk about activation energy. Okay. Before I start with talking about activation energy, I forget to mention this. Okay, an exothermic reaction, because the reaction is creating heat, it will be given to outside. So temperature of outside is going to go up. Like, for example, you turn a heater, or like in a gas, say, heater in your place or stove. If you leave it working for a while, very soon you will see that your room or your house is going to get warmer because the reaction, methane, is creating heat, and heat it will be given to outside. Well, in endothermic, it will get heat from outside. Like, for example, melting ice. Ice, if you hold a glass of water that it has ice in it, you will feel that it's cold. Why it's cold? Because it's taking heat from you to melt ice. Okay, so an endothermic reaction is taking heat from outside, and outside is going to get colder. Okay, now let's talk about activation energy. Activation energy, we said the barrier. We need to provide that barrier. The higher the barrier is, the slower the reaction will be. Or the lower the activation energy is, the faster reaction will be. So between these two, I have one on the left side. It has smaller activation energy than the second reaction. So I'm going to say the first reaction, it will be faster because I need less energy to initiate the reaction. Next thing is, what's the effect of the temperature? In order to have a chemical reaction, we need to have collision. Okay, we need to have collision. As you increase the temperature, velocity of objects will go up, and this is the proof for it. Okay, so I say as you increase the temperature, velocity will go up. Why? Okay, velocity is subject to temperature. Okay, velocity is subject to temperature. This is not volume. I put vector on the top of it. So velocity is subject to temperature. We say kinetic energy is equal to half of mass multiplied square of velocity. This one will be kilogram, and velocity it will be meter over second. So I get kilogram multiply m2 divided by s2, and that's going to be equal to joule. Okay. If temperature temperature goes up, velocity will go up. That means the kinetic energy will go up. If an object has higher energy, it will move faster. And if that object moves faster, it will get more collision. More collision means higher chance to meet the activation energy. Higher chance to meet the activation energy. Remember, we need to meet the activation energy to get the product. Okay, so we need to give it enough energy to meet the activation energy. So when the temperature is low, I have only this area. Only that area is available. It has enough energy to pass the activation energy. As I increase the temperature, yes, the max is going down, and I will say why it's going down, but number of molecules that they have enough energy to pass the activation energy will go up. And this is the threshold that you need to meet. Okay, so the threshold is, forgive me, this is the threshold. Threshold is here. We need to meet that threshold to technically initiate the reaction. Now, why the max point is going down by increasing temperature? Okay, put it this way. If you're driving 60, 70 miles per hour, you have good control of your car. But if you start driving 85 or 90 or 100 mile per hour, then I'm going to say there will be a chance to have maybe a car accident. Why? Because you are moving faster. It will be harder to control the car. And when it comes to molecules, when they move faster, we say there is higher chance to have collision. And if we have collision, we're going to maybe get more energy or lose some energy to whatever we had. And in that case, we say the max is going to go down. Okay. So we know we need to have lower activation energy to have faster chemical reaction. And if we increase the temperature, reaction will be faster if we increase the temperature.